So it's 7:30. Should we start?
Okay.
So, okay. So, good evening, everyone, and we are now starting this keynote speaker session of YouQ. And today, in this session, today the first speaker is Professor Ana Sanpera from Universitat Autonoma Barcelona, Spain. I'm really happy to introduce Ana in this program, and I'm really happy that Ana agrees to speak in YouQ 2020. I must add that I started working with her during my postdoctoral time, and I got a lot of inspirations from her. We have a lot of scientific discussion, and at the same time, I think we have a lot of discussion about gender equality in science. And I have learned so many things from her, and really, she's one of my inspiration. So, Ana, please.
Thank you very much, Aditi, for this nice introduction. And thank you for this invitation. It is my pleasure to collaborate in this Q2 2020. And I would like to talk about today, what I'm going to present is the recent work that we have done about the storage capacity of quantum neural networks. I must say that this work has not been even posted into the archives. Probably it will be posted in the last week. And since this is a long talk, I will try to be very pedagogical, and this is a talk for the students. So I will skip under the carpet all kinds of calculations, and if there is any question at the end, you can go through, but I would like very much to give a talk which is introductory. So first of all, I would like to, oops, how do I move now? Just a second. That's very nice, but I cannot move in this now. Whoops. How I go back? This is to use this PDF.
So how did you?
Now, yeah, okay. Now that's working because I had to put it. So first of all, I would like to dedicate this lecture to the memory of Peter Vitek. So many of you probably don't know who is. He was a very bright scientist working in quantum learning and quantum learning machine who disappeared last year indeed in India when he was in trying to climb on the Everest, and he disappeared and his body has never been found. But he is one of the fathers of quantum machine learning. And I just want to mention or to read exactly one of his sentences. He has a very good book that we are all using, which is Quantum Machine Learning, and that he says quantum is next, not just quantum machine learning, but quantum computing in general. Breakthroughs are happening every day, both on hardware and on the kind of algorithms you can build with quantum computers. But it's going to take another 10 years until it gets into public discussions and start to disrupt industries. The companies as seen today are going to be the ones that eventually disrupt industries. Peter was an academic. He was already in a, I think, tenure track at the University of Toronto at that time, but he was also very interested in industry, and he had founded a couple of companies. So what I'm going to talk today. So I want to explain a little bit first to introduce the subject. So what are classical neural networks? So what is a neural network? What is the learning capability of a neural network? And what is the storage capacity of a neural network? And then we will move to quantum neural networks, which I will explain very briefly what is a quantum neural network. And in blue, I have written here the things that we have been working on. One, it's what is the storage capacity of a quantum neural network. And the second point, it's what is the Garner's program for quantum neural networks. And I will explain you what it is, this program, and what it is important. So let's go back to time and start by a classical neural network. So what is a neural network? Well, first, what are real neurons? We all know that the brain is a network of approximately 100 billion of neurons, which are cells which are capable of receiving, processing, and transmitting information via electrical and chemical signals. Indeed, the synapses is information flow that it goes from one cell to another cell. And I have to mention here that the discovering of neurons as these cells was done by Santiago Ramón y Cajal, which was, I think, the only Spanish scientist which was awarded with a Nobel Prize, okay, in which he was depicting how the cells in the brain, the neurons, they connect to each other. And this is, well, and his graphs are still used. And this is a very schematical point of a neuron, which it has the axons, then it has the dendrite where the information is sent, okay? And then there is this part of here where there is a chemical potential between the two neurons. If the neuron is active, then it sends information to the synapses, which is received by this other neuron, okay? Let me tell you, since this is also a students' conference, that Santiago Ramón y Cajal was a Spanish neuroscience and pathologist who discovered how neurons works, and indeed he won the Nobel Prize, and he's one of the pioneers of modern neuroscience. But as a child, he was a terrible student, okay? And he was transferred from one school to another many, many times because his behavior was considered to be poor, rebellious, and he had something very positive, which was an anti-authoritarian attitude. For that reason, at that time, he was put in jail at the age of 11 because he constructed a cannon and decided to bomb the neighbor's garden. And the police were not happy, so he spent a few days in jail for this reason. So what artificial neurons are? So of course, artificial neurons, what they want to do is to simulate, and it was very clear. So we are talking about beginning of the century. He was awarded the Nobel Prize in 1906. So artificial neurons was a model, a mathematical model, which was conceived in order to describe the biological neurons. And the first artificial neuron was what it's called the McCulloch-Pitts neuron, which was in 1943, in which they decided that they can simulate mathematically what a neuron has. So a neuron has the inputs that it receives from another neurons. So here in this model, these are the inputs. And then it has to have a mechanism because the neuron can be active and fire a signal, or can be not active and therefore doesn't react. So you have here kind of a function, which sometimes is called an aggregator function, which depending on this function, the neural takes an output, which is binary, which is 0, the neuron doesn't fire, or 1, the neuron fire. So this is exactly a single model of a network, or if you want, it's a neural network of only one neuron. And this here is Pitts. No, here, sorry, it's McCulloch and Pitts. So this simple model, it was very soon realized, then can do a lot of things. So if you take the logical functions, for instance, if you take, let's start by this small pan here, and you want to symbolize how is the AND function, which is a function that it gives us an output 0 unless for any input, unless all the inputs are 1. And you put here as a theta function 3, and you add the values. So you have that if the input of the first cell, it's of the first neuron or the first input, these are binary inputs, so it can only be 0 and 1. So if this is 0, 0, 0, it's smaller than 3, so the result is 0, and so on and so forth. And only when the 3 inputs are 1, okay, then the result will be 1. So this is an AND function. And you can even do it simple with only 2 inputs, and depending on the value of theta, you can construct an OR function or a NOR function or a NAND function, just changing the value of the threshold. And as you know, or maybe you don't know, but for instance, the NAND function, it's a universal gate. So in principle, with such a simple artificial neuron, you can construct all possible gates in classical logics. And this was quite relevant and important. So a little bit later appeared a version, which is, I have to say that both Pitts and McCulloch, they were not physicists. One was a neurobiologist and the other one was a logician. So that's the reason that they immediately realized that with that model, they can do all the logical gates, and they found it very interesting. So the next step came in 1953, which is the Rosenblatt perceptron. And it's a little bit different because it's again a network with a single artificial neuron, but this artificial neuron, it's the basis of today's neural networks, okay? Until the mid of the 80s, that was the state of the art on neural networks. So what is different here? Well, it has several things which are different. First one, it's that the inputs can be any number, so it doesn't need to be 0 and 1. But in order to simulate better what a neuron does, he put some weights here. So each input, it's weighted with some weight, and then you have a function here, and this function has a threshold, and the threshold will be 0, 1. It's again a theta of Heaviside function, and you will be an output. So in this term, we can write it like that. So I have a function, which is the result of that it will be 1 if the weighted inputs, so input 1 with weight 1 plus input 2 with weight 2 and so on and so forth, it's larger or equal than a value threshold, which is theta. Okay. And it was soon realized that if you do machine learning, this perceptron, it's an algorithm for supervised learning of binary classifiers because it has this output, which is 1 and 0. So it's able to do any linear classifier. Okay. So this was really a very strong point, and a little bit, so that was at the end of 57, and it was a little bit when the field of artificial intelligence and machine learning was starting to become more and more active. So nowadays, if we want to define machine learning, I will say that the best definition I have found is that machine learning is the science of getting computers act without being explicitly programmed for. This is a definition of the Stanford University, and I found that it's very appropriate because what machine learning, so what we have always done is that if we wanted to calculate something, so we prepare a program, we do the program, and then we get our calculation. Machine learning doesn't aim to do that. On the contrary, what it aims is to train, okay, the computer so that it makes the calculations without we programming. And how does it do it? So it does it by learning and by giving a lot of data to the computer and showing which data is good and which data is bad. So you want to distinguish with cats and dogs. So you give a lot of pictures. So you give a training set in which you put a picture of a dog and you say, this is a dog to the computer. And if there is a dog, you make the computer to make a 1. And if it's a cat, make a 0. And after many cats and dogs, when you put, this is the training set, so the computer has been trained, so acquires more knowledge about what it's a dog and what it's a cat, in such a way that when you give, after this training data, a picture of a dog or a cat that has not been in the training data, the computer should do it. But what has been the last boom on the machine learning and also in quantum machine learning, it's deep learning. And deep learning, it's a multi-layer feed-forward neural network, like it is explained here. So you have, as before, like in the perceptron, you have inputs. So this is how it was the perceptron. And now what happens is that you don't have only a single neuron, you have a network of neurons, and you have several layers. And the computation proceeds this feed forward, and at the end, you have an output. Okay? And deep learning is a technique that has proved to be incredibly successful in the last years. And indeed, it proved to be incredibly successful because the GPU of the games, okay? So the industry of the games, since everybody was playing games in the computer, the industry of the games started to program, and then they realized without understanding why, because it's not clear why that works, because at the beginning, this is not a new idea. So it was thought that if you have more layers and in some way always trying to simulate how the brain is, the neural network will be more powerful, but it became to be very complex and the results were very poor. And now it's known that if you have this feed forward, the propagation always go from the input layer to the output layer without going back in any case. You can have results which are very, very amazing. So I have to say that a little bit later, after these perceptrons, we are talking about the 80s, 85, there was this Minsky and Pepper-Nogo theorem in which he showed that the perceptron or any extension of the perceptron can only solve linear programs. So it was this Nogo theorem. And in some way, this result killed the field of machine learning and artificial intelligence for almost 30 years. Okay? And because it had been an explosion, and we will see why, and until it was not realized that there is this multi-layer feed-forward networks work, the field was just, it froze, right? So very few people were in the year 2000 or in 1900 working on neural networks. So let me tell you about some neural networks that we are going to use later. So what is an attractor neural network? So we have these networks of neurons that they are connected always on this way. And we talk about attractor neural networks like a dynamical network that evolves towards a pattern over the time. Okay, so it has a point and it goes over the time. And these attractor networks have been used in computational neurosciences for a long time in order to model always the brain. So how the associative memory it works, because you get to a point, I will explain what it's this minimal of energy, this attractor, which is a point where all the networks reach at the same time. Okay, so these attractor networks have a set of nodes, which they can be represented as vectors in a dimensional space. And over the time, the networks tends towards one of the predefinite states, and these are called the attractors. So let me put an example, and that was in the 80s, was again a big step when it was an example of an attractor neural network, and that it was done really with physics. So this was John Hopfield, which is here in the picture, who decided to say, listen, imagine that you have a Hamiltonian, which is like that. So you have interactions, and on these interactions between the spins. But these spins, we are talking about classical spins, sorry. We are talking about classical spins, so these spins can only be up and down. Right? So they are not quantum spins, they don't have any commutation rules, so it's simply up and down. And now you make these spins to interact with interaction Jij, which is interaction between the spin I and the spin J, and this summatory goes over all Ij here, it's wrong. And you ask, this is not important, but in order to make very simple, that if the neuron I interacts with the neuron J, this is symmetrical. Okay? So otherwise, these interactions are completely random. They can be positive, they can be negative, and so on. And now, what do you want to know? It's which are the stationary states of such a Hamiltonian, okay? So if we look, which is the energy of this, so this is a picture trying to show how is a neural network in which each spin, if you have, or what is a spin glass, so the Hopfield model, if you have interactions which are all positive or all negative, you will have something which is order. So if all the interactions are positive, of course, this will be a ferromagnet. So all the spins will have the minimal energy because this will be positive. You have a minus here. So to lower the energy, you will require that the spin I is oriented with the spin J. This is a ferromagnet. But if these coefficients Gij are random, some of them are positive, some of them are negative, what you have is a spin glass in which a priori there is not order. There is not order, not a priori, there is not order. So if you look how is the energy of such a Hamiltonian, okay, as a function on how are the spins, so I write here my spin configurations, we will find that this Hamiltonian has some minima which are stronger than other, and a priori it doesn't have, here I have depicted one minima, but it doesn't have a defined minima. It has several minimas, and we don't know, it's a problem which is impossible, well, very hard to find if there is a lower bound of the energy. But we know that there are some small values. So the system, what we like to do is to go to one of these values, okay? So how does it work? How do you get one of these values of minimal energy? So let me write again the Hamiltonian. So you have that it's -1/2 because the interactions are symmetric, Si, Sj, and imagine that these spins, they depend on time. So if you want to have a minimal of this Hamiltonian, if you want to do it dynamically, you have to ask, or the solution of that, it's that the spin Si has the sign of this part of the Hamiltonian, okay? Why? Because if I single out here Si, okay, and this part it's positive, then the spin Si has to have the same sign. So it will be positive and positive. I don't know how they are. I only know that the sum of all of them gives me a positive thing. So this guy has to be positive because positive is positive, with this minus is negative, so the energy lowers. And if this guy is negative, okay, so the sign of this thing it's negative, I want that this guy is also negative, the spin points down, because it will be negative times that, negative the rest, positive with this minus negative. So the solution to find which is the stationary states of such spin glass, it's to have states that they are like that. Okay? And now, if you allow them that they change on time, what it will happen is that at some time, the whole spin of configurations will be here, but in order to diminish the energy, it will be updated every time like that, and it will go down, 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 down until it reaches an attractor, a local minima of energy, which means that this attractor is like a memory, because wherever I start from, if I'm close to this attractor, I will run to this attractor. So this is like an associative, and when it's here, it will not move, okay? Because in order to move, it has to increase the energy, and the system doesn't want to do it. And the same will happen here. It will have another attractor, which has higher energy, it doesn't matter, but if the system initially is in these conditions, it will go down, 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 and it will stay here. So when you see these things, you see that this is a kind of, is an attractor. This is called attractor neural network because the network goes to this basin of attraction, okay? And I have many of these basins of attraction. So the thing that I want to ask, and this is what we can say, this is a memory. So if I train my neural network so that when it's in this position, okay, so all the spins that I hear, I have n spins, but they are in this configuration, I can say, okay, I can associate this configuration to something. And the system will go either here, or will go here, or will go to another basin of attraction. So when it does these things, this is a kind of a memory, and it's associative memory because you need all the spins at the same time, that they talk to each other and they get to these points. Okay. So now if you want to say, well, what is the storage capacity of an attractor neural network? What I have to ask is how many patterns, we can call it patterns, we can call it memories, we can call it stationary states, they can be stored in the neural network. So let me call this psi of u mu as configuration of spins, okay? Where I have I, the spins, they go from 1 to n. I have classical spins. And I want to know how many of these patterns exist. So mu goes from 1 to p, okay? So the pattern of the sigma psi I mu will be corresponding to these signs of here. So this is an important question because if we want to use a neural network for learning and for keeping memory and recognizing things, so we have to know how this neural network can be learning. So when we talk about learning, what do we mean? Well, learning means anything, adjusting, for instance, or modifying the interactions between the spins, or putting, for instance, so this is how I have to change the interactions, or putting an external magnetic field or whatever, okay, that I can do to my physical system. Now I have to say, if I want to store P patterns, okay, or memories or stationary states of this form, these are the patterns. I have P different patterns, so I can learn P different things, or my neural network has P different attractors, where the attractors, these points, which are the attractors, so these are the configurations of the spins of the attractor points, of the minimal of energy, which they are given by this sign of the sama pam pam. How can I update my neural network that the neural network, so I start with completely random configuration of spins, random configuration of the interactions, and now I have to change at each time, okay? So I calculate with these random configurations, which are the patterns. And now what I have to do, once I have the patterns, these ones of here, is that I have to teach to the neural networks that the interactions between the spins have to be of this form. Okay, so for each pattern, I have to put this kind of interactions. And this thing of here, these patterns, what are these patterns? Well, these patterns can be random independent distributed variables, okay, which they have probability that the spin points up in one of these completely random independently prepared distributions. The spin points up with probability 1/2 and points down with probability 1/2. So it's a network in which I don't have any bias. Okay, and this is a Hebbian rule for learning. It's one of the rules for learning, but that was very interesting. So what we have done now, if we have something like that, now I can calculate how many patterns can be stored, because I say, okay, I calculate, I give a set of patterns, for instance, okay, and now I change the interactions, okay, with this set of patterns. I set the interactions that I can reach these patterns, and now I calculate how many patterns I can have. So if I have n spins and I teach my spins how to go to these stationary states, I find that if P is much, much smaller than n, storage of some memories, so I have several attractors, it's possible. What does that mean? It means that I have several minima and I can teach my network to go to some of these minima, okay? Indeed, it can be shown that how many storage patterns I can keep like that. Well, I can keep alpha times n, where n is the total number of spins, and alpha, it's smaller than 1. Okay, so if I have 10 spins, I can probably approximately keep one pattern, only one. If I have 100 spins, and I want to know how many memories I can associate to these 100 spins and make my system learn different memories, different patterns, which each pattern will be a different thing, I can do approximately 10. This alpha is of the order of 0.01. Okay? If I have 1,000 spins, I can have 100 and so on and so forth. So these attracting neural networks are very good for pattern recognition and allows to address the memory, and this is important. So this was the state of the art in the 80s. And until in 87 and 89, there were two contributions from Elizabeth Garner, which was a very young postdoc who indeed died at the age of 31 years old, I think, okay, when just she was in a very creative form, which twisted all this neural networks program completely up down. And everything which is done in neural networks, not so many people know, but it's beneath her contributions. So what she says in very simple words, it's that it's not important to search which are the stationary states of the model. This is not relevant. What is relevant if one wants to use its neural network is to fix a stationary state, whatever it is, and to look how many Hamiltonians have such a state as a stationary, okay? So this is conceptually very different, but simple. So before, what the people were saying is Hopfield model, I give you a Hamiltonian with these Jij's, which are random, and I look which are the stationary states, okay? And now I give a learning rule for my system, and I see how many of these stationary states I can access to it dynamically. And now I have these patterns, okay? And Elizabeth Garner told us, no, this is not the way to think. The way to think is that if you want to have something which is really a good memory, it will be a good memory if this pattern can be reached from many Hamiltonians. And it will be a good memory if the number of Hamiltonians that allows to reach this pattern, it's good, because I don't have to worry then about the Hamiltonian. And this is very important. While if the relative volume of Hamiltonians that lead to this specific pattern is small, this is irrelevant because it will be a bad memory. Okay? So this is more or less what is a very, very preliminary resume of what is these neural networks classically, and what are these attractor neural networks, and what happens up to the 80s. And she did also something very important. It's that she put here statistical physics. Okay, so she was doing the thermodynamics of these neural networks, which is very important. So if we want to go from classical neural networks to quantum neural networks, well, this is kind of simple, no? It means that instead of having inputs, which will be neurons and then hidden neurons and outputs, I will have inputs, which will be quantum states. Then I will have that all these synapses are operations, and then I will have another layer of operations and another layer of operations. So these are the hidden layers. And then at the end, I will have my output neurons, and then I will do a measurement, and that will be my result. So conceptually, it's very easy to go from classical neural networks to quantum neural networks. So then what we wanted to know, and we were interested, and this is the contribution which is original from us, okay? It's what is the storage capacity of a quantum neural network. So if I have a classical network with n classical neurons, which are classical spins, which they can be up or down, but they cannot be, they are not quantum bits that they can be 0 and 1 at the same time. They can be either, if they are classical, 0 or 1. I know that the storage capacity is approximately, in the best cases, 10% of the size of the network. So what happens if you go from classical to quantum? Can a quantum neural network storage much more information? Can you have much more memories? And this is a question that it was already asked. I think first person who asked this question was Maciek Levenstein in '94, who was trying to analyze the storage capacity and the Garner program, encoding neurons as a qubits. It was an attempt because it was not any result which was conclusive, and it was just a first attempt. And then a few years later, it was when it started to be all this boom of quantum information, people in machine learning, Ventura and Martinez, they decided to use a quantum search algorithm, which indeed was Grover algorithm, okay, to show that if you have a classical neural network, so still you have classical spins, but now what you do is search with a quantum algorithm, you can increase the associative memory exponentially, okay? It's a very complicated paper, but they show that this is a law. And then in 2018, there was another example of an exponential increase of memory by Patrick Prevost and so on the group of Seth Lloyd, that they say, well, if I make this Hopfield model, which is very simple, as a quantum Hopfield model, and for a very particular case of the interactions that I choose, they show that they could increase the storage capacity exponentially. So what we have done, and this is our contribution, and I have to say that this is motivated, and it was important. It was Maciek who brought us this problem to us. So, and say, let's redefine it again and think about what is the storage capacity of a quantum neural network. Okay, and this is a work in collaboration with Maciek Levenstein, with Ekaterina Gracea, and with Valentin Kasper and Albert Aloy, which are in the ICFO, and with Andreu Riera Campenya and myself, which we are at the University Autónoma of Barcelona. So now we have to think quantum. Okay, so let's think a little bit quantum. So what is the storage capacity of a quantum neural network? Well, any physical process, we know that it's characterized by a completely positive trace-preserving map lambda. So what is this map? The map lambda, which goes from A prime to A, it's a map which acts on quantum states. That means operators, bound operators on a Hilbert space of dimension, whatever, A, to another Hilbert space A prime. Sorry, the prime should be there. So that if I have a state which lives in the Hilbert space, this should be no prime, sorry, in here, and I apply my map, I will go to my Hilbert space A prime. If this map, it's a physical map, it has to be completely positive and trace preserving. What does that mean? Well, that the map is positive means that for any state that it's positive, applying the map will give me a positive state. It has to be like that. If not, it will not be physical. That it's completely positive means that if any extension of this map with identity has to be also positive. So if I have my state, rho of A, and now I put a composite state with another state, and I apply an extension of the map, the result has to be also a physical state. And if the map is trace preserving, it means simply that the trace of the map has to be equal, applying on one state has to be equal to the trace of the original state, so equal to 1. So if we want to think what is the storage capacity of a quantum neural network, we can think it in the following way. What is the maximal number of stationary states a non-trivial map can have? This seems a very simple question, but for some reason that I don't know, nobody was asking like that. So everybody knows that a map has for sure one stationary state. This is the steady state of the map. But how many stationary states can have? When I mean not trivial, I mean that this map cannot be the identity, because obviously the identity maps any state on itself. So it has all possible stationary states. So the answer to this question is that there exist non-trivial maps that act on an n-dimensional Hilbert space that have n orthogonal stationary states. This is the first theorem that we prove. And I'm not going to prove it, but I want to show you a little bit more. Okay, so we are asking, there are maps which are completely positive and trace preserving. So they correspond to physical acceptable operations that they have n orthogonal states that they are stationary and they are not the identity. And the answer is yes, they are. Okay, so let's see how it can be that there are these maps that they have n orthogonal stationary states. So in order to do that, we have to assume the following. Okay, we are going to consider that we are in a Hilbert space of dimension n. And I don't care how is this Hilbert space. I don't know if these are qubits or n bits, so I don't care. The Hilbert space has dimension n. I know that quantum states corresponds to positive semi-definite trace 1 operators. I know that CCP maps, CPTP maps correspond to linear maps between two Hilbert spaces. Okay, so it goes from A prime, Hilbert space A prime to Hilbert space A. And we know also that such maps, they can be conveniently characterized by an operator via what it's called the Jamiokowski-Choi-Sundaram isomorphism. So I can have a map which transform operators, or I can have a Choi operator which has the following form. Okay, the Choi operator E is a Choi operator which acts in a composite system, HA prime, up here. And it has to fulfill that its Hermitian. And moreover, it's going to be always positive semi-definite. And the isomorphism works as follows. If I have my map, which goes from A prime to A, So it transforms an state which lives in A prime to an state, physical state, which lives in A. This is equivalent to tracing over A prime my Choi operator acting on row A prime transpose. So in this way, I go from given a Choi operator, I obtain the map. And if I want to go to the other direction, because this is an isomorphism, I know that the map, okay, which acts in A prime A, I can write it always like the identity acting on A times my map, which is in 2 copies, okay, be careful because now it's A prime, A2 primes, acting on the maximal entangled state, which is of the form I in A, I in A2 primes, J in A, J in A2 primes. So this is very well known. And so in order to find if there are maps which have n stationary states, we are going to look if they are operators, corresponding operators, that they have this n-dimensional space. So I told you that I'm not going to prove it, so I'm going to give you the results. So let me remark again that if a map is a completely positive trace-preserving map, that means that the associated operator is Hermitian and defined positive, and the fact that the trace is trace-preserving, that means that when I trace over my system A, my Choi operator, I have to have the identity. It has to be now a matrix, okay, because this is acting in a composite state, so this cannot be the number 1. It's the identity on the space A prime. Okay, so the theorem well stated is like that. There exist non-trivial maps such when I apply these maps to linearly independent states, they give me linearly independent states. How many? N linearly independent states. These maps, they exist. How are these maps? Well, I give you the form of these maps. One has to try it, but this is the form of the map. Oh, this is the form, let's be correct, of the corresponding Choi operator. And if you look like that, maybe you don't see anything, but it's kind of very interesting map. Okay, it's a map that with weight 1 has diagonal elements. So these are the diagonal elements. Now this is an orthogonal basis. So I am in my computational basis 0, 0, 0, 0, 1, 1, 1, 1, and so on. So if I have my matrix, I will have 1s in the diagonal principal, and then outside the diagonal principal, I will have only contributions of this form, mu, mu, nu, nu, 0, 0, 1, 1, with this weight of here, 1 plus alpha of mu, nu. And this sum, it runs for mu differem of n. Okay. Now, since I know, because this originates for a map that's a completely positive map and trace preserving, so the Choi state has to be positive, that means that these coefficients of here have to fulfill this condition. We will see it much easily. Let me put an example in which I have a Hilbert space of dimension 4. Okay, so for instance, 2 qubits. How is this map? This map is only in the diagonal principal mu, mu, nu, nu. So 0, 0, 0, 0, 1, 1, 1, 1, 1, 1. The other ones are 0, 0, 0, 1, nothing. Sorry, this is the diagonal element 0, 1, 0, 1, nothing. 1, 0, 1, 0, nothing. And this one. And of diagonals, it only has these elements. Okay, 1 plus alpha 0, 1, 1 plus alpha star 0, 1. Now you see that in order that this matrix is defined positive, the determinant has to be positive. So the determinant is 1 times minus that has to be positive. Therefore, this guy of here have to be smaller or equal 1 for all mu nu. And this is the map. So if you, this is the Choi operator. Now, if you look which is the map corresponding to this Choi operator, you will see that this map will have 4 stationary states, okay, which will be 0, 0, 1, 1, 0, 1, and 1, 0. Good. So what we can learn from this kind of maps? Well, we can learn two things. The first thing is that if such a map exists and has n stationary states, for sure it should be many more maps that are able to have p smaller than n stationary states. Because obviously to put n stationary states is a very strong restriction. So if I reduce the number of stationary states, I will have many of these maps. And the second thing that we can learn from here is that, or we can ask ourselves, can I have a map that can store or has as stationary states more than n dimensional states? So if I have p equal n plus 1, so if there exists a map such that it has these n stationary orthogonal states from 1 to n, and there exists also a state, this one, that it's also stationary state. And since this is an orthogonal basis, this state has to be of this form. Well, if that map exists, that map is the identity map. So it cannot be any non-trivial map that stores more than n orthogonal states if I have a Hilbert space of dimension n. So what does it mean? Well, it means that a classical attractor neural network, if it has n bits, we have seen that it can store of the order of n patterns. A quantum attractor neural network, if it has n qubits, it can store 2 to the n patterns. So quantum neural networks have exponential storage capacity, and this is important. But now, this was never proved rigorously, and this is very nice. It's a result which is very easy to prove, especially if you have Maciek Levenstein nearby and you have some problems and then he sees how to solve it. But now the thing which is interesting is, no, let's think really. So if we say classically that what is important, and Elizabeth Garner's told us that what is important is not that how many patterns my system has, but if I fix a pattern, how many Hamiltonians lead to that pattern? Now we have to make the same question quantum, okay? And how do we do this question quantum? Well, there is two questions we can say. First one, in the space of completely positive trace-preserving map, how many do they have maximal storage capacity? Okay, because maybe we have one, and this is not very interesting. Of course, it will not be many because it's very restrictive to have n states which are stationary states. So, but we would like to know how many. And we can ask also another question, which is the following. In the space of CP-TP maps, how many of them they have a large storage capacity? Maybe they don't have n, but maybe they have a number smaller than n, but still large. So this will be also important. No? And now we have to think how to calculate that. And this is not very easy, and one starts to be a little bit metaphysical, because how do you count that? Of course, you cannot start to count all the maps that you have. You can be tempted that if you look like that and you see, wow, listen, in this map, I can choose here alpha 01 arbitrarily if this condition is restricted. So there is infinite of these conditions, and this is true, but that it's not the solution, because this kind of map, if I look in general to all CP-TP maps of dimension 4, will be very small number. And this is what we are asking. Okay? If I look in all the space of the CP-TP maps, how many have this maximal storage capacity? So if we want to ask this question rigorously, we have to say, which is the relative volume of CP-TP maps acting on dimension n such that they have m smaller than n stationary states as compared to all CP-TP maps acting in this Hilbert space. Okay. So how one calculates that? Well, I have to say, this is not very easy, and it has taken us several weeks, and we have found many different results, but until we found out how to do it. And this is the result. So first of all, one looks in the literature, and the total volume of CPTP maps, it was calculated many years ago by Straszek, Garner, and Karol Tchaikovsky in this archive paper, where they show the following. First of all, imagine that they calculate first which is the radius of a ball of maps acting on n-dimensional Hilbert space, okay? And they realize that when n goes to infinite, the number of maps, the radius of this ball goes like e to the minus 1/4. Okay, so it's small, but it's not zero. Now they calculate here how is the volume of these CTPT maps. Okay, and this is this formula of here, which sounds, well, it's simple once that you learn it. So of course, it has to be, if the radius is like that, the volume of the corresponding sphere will go with the dimension, okay, d. And then you have, this is the volume of the unit sphere, this is the gamma, it doesn't have importance, and this is the unitaries, it doesn't have importance. What is this d? Because we are working in a Hilbert space of n dimension. The d is the dimension of the space of CPTP maps, and it's n to the 4th minus n to the square. So of all possible maps, okay, the dimension of the completely positive trace preserving, if I am in a Hilbert space of dimension n, it's this one. So having that, now what do we have to do? We have to go a step further, and we have to estimate which is the volume of all these CPTP, I always write it bad, but it's trace preserving maps that they have, that they have m stationary states smaller than n. So if we look how it was our Choi operator, we look that these elements have to be 1, okay? So this is the matrix that we were looking. So it's this matrix of here so these elements have to be 1 here and 1 here, okay? So we have to impose this condition, okay? And we are going to impose this condition, but we will assume that we can have an error in the map. And this epsilon, it's more or less the accuracy. And when we calculate that, so this is the volume of all completely positive trace preserving maps that they have m stationary states, it goes like that, okay? So I have to choose m stationary states out of n, and I don't have any order. So I have a binomial factor here. I have to weight each of these m stationary states by the accuracy, epsilon, which has to be small. And I have to calculate to weight that by all the completely positive trace preserving maps that act in d minus m, because I have put this restriction already on these m stationary states. Well, you look at this formula, you work a little bit with this formula, it doesn't have any importance. And then you get that the relative volume of these maps goes like 1 divided by m. And this is a very good result because it tells you that there are a lot of maps. So of course, the volume of maps reduces when m increases. And this we know it because every time it's more difficult to find maps that fulfill of these conditions. But it reduces very slowly. It reduces like exponential, right? Or the log decreases just linearly, which means that there is a lot of these CPTP maps which have m smaller than n stationary states. And therefore, quantum neural networks have exponential memory, but on top of them having exponential memory, which is interesting, there are many maps that they can do that. So therefore, this is really what it's called a quantum advantage. And with that, I will thank you very much for your attention, and I would like to finish. Thank you.
Thank you very much, Anna, for very interesting talks, and it's very nice. So now we ask some questions because there are some people who have asked some questions. So the first question is from Ribhu Gupta. He asks, stationary states in classical neural network are states which have lowest energy and may not be the same as the initial state. why are we considering stationary state in quantum neural network as the ones which are the same as the initial state?
Well, a stationary state, a map is a dynamical thing that changes a state. So when I apply a map to my state, it changes. If it doesn't change, this is a stationary state by definition. So this is clear. In the classical case, okay, we are not talking about stationary states because we are not talking about transformations of the map. We are talking about Hamiltonians, and we are looking which are the states towards the system will evolve. And we know that this will be the state of lower energy, okay, because the state likes to be in the lower possible energy. Therefore, their stationary states or patterns are what we call attractors. And of course, we have to have a system that it has many, because if I have a system which has only a lower state of energy, that there is no game. The system will evolve to this, let's say, ground state and will not move from there. So it will not be useful for storing memories. To storage memories, I have to have different states to have different memories.
Okay. Review, do you want to add or ask something more?
No, ma'am. Thank you for the answer.
Thank you.
Okay. So the second question is from Kapil Sharma. He asked, how do you train the quantum neural networks?
It's a very good idea that I have to say no idea. I mean, I don't know it. Thank you very much, but I don't know it, how to train it.
Okay, so then the third question is from Ujjal. The identity is trivial. Are unitaries also trivial, as that is only a change of basis?
That's a good question. No, they are not trivial, because although it's a change of basis, the unitary, although it will be very, very reduced kind, because you have to put extra conditions if you consider that your map is a unitary. But a priori, the unitary, the only one that will have stationary states will be the one who is the identity in this sense, because you change the basis, but you want to have that if I have this state, when I apply my physical system remains to be this state. So if you do the unitary, you are right, you are changing and you will have another of the orthogonal states, okay? You don't have to have the same. But if you want that all of them remain the same, then your unitary is the identity. There is no other way. So imposing that on the, so there is no, yes, it will be, because it has to be all orthogonal and it has to be n states, and you have, it cannot be another one. So I understand what you mean, but the unitary, when you change the basis, doesn't preserve the stationary states, changes, relabel them, okay? So it can be also useful, but you want to know that if you started from this state and you do a physical map, you end up in this state, not in another one of your orthogonal states. That's nice, please.
Okay, then the question is from Shiladitya Mal. Is more number of stationary state imply more memory?
Yes, imply more memory. Yes, of course, because
then,
now
yeah,
more memory in the following thing. Okay, so imagine that I was saying with the initial artificial networks or perceptron, you have just two outputs, 0 and 1. So you do linear classification. So let's say, very badly speaking, okay, if you want to do pattern recognition, if you are able to storage more patterns and to retrieve these patterns, you have much more memories. Okay, so you can recognize many different things. If you are able to storage one thing, that's useless, okay, because you cannot distinguish. So what do you want is to distinguish between different things, for instance. So at least you have to have two patterns and say, okay, I associate this pattern to cats and the other one to dogs. And then if I go to this pattern, I know that my state will be a dog. What I'm reading is a dog, and the other one will be a cat. If I have many other things, I can do more. So I can say, I want to know if this is a dog which is brown, this is a dog which is white, this is a cat which is brown, this is a cat which is white. So I need 4 memories because I have 4 patterns which are different. So to have a larger memory implies to have more patterns that you can associate, yes.
Yeah, and he also has a question that CPTP map also includes measurement. How measurement can be useful?
Good question. Never thought about that. Let's say that we wanted to do a rigorously prove this, that there exists. And I think it's nice because there are many applications of that. Okay, so this is in the sense of neural networks, but we are doing it completely general. So imagine that you have any problem which has nothing to do with learning and so on, and you want to know how many stationary states your map has, or you need many stationary states for something. Okay, so in this respect, I think it's very nice because if you ask me, give me a map which is CPTP and that has 24 stationary states in a Hilbert space of 50, I give it to you, okay, or 27 and so on. Of course, 2 stationary states is very simple because it's very little restrictions. But we never thought on the action of measuring, which is important. No, I cannot say.
Okay, so then there is a question from Ganesh that thanks for the talk. And then he asked, compared to a normal storage, a normal memory, why is it advantageous to store data in classical or quantum neural network?
Sorry, say again. So compared to
a normal storage, a normal memory, why is it advantageous to store data in classical or quantum neural network?
Okay. Well, the advantage is that with the same number, so if you are classical, and let's put a physical system which are spins, it can be anything, a bit, whatever a bit is, okay? And you have n bits classically, and you want to classify different things, so you want to have this pattern storage. You know that classically you can storage approximately 10%. Okay, you can have as a storage 10%, the capacity is 10% of the size of your network. So if you have 5 bits, if you have 10 bits, you can storage 1 pattern. If you have 10 qubits, you can store 2 to the 10, which is 1024 patterns. So it's different.
Okay, so then Tanaya also asked a similar question as far as I understand. Is there any comparison on how fast the classical, okay, a bit different, how fast the classical and quantum network reach the stationary states?
Oh, no idea. I think that will depend very much because, of course, we talk about maps without associating, so it's very abstract. No? So if you say, I have to give the Krauss representation of the map if I want to know how this map is and to know a little bit more. No? So we never look, which is an interesting question. We never thought about this, the Krauss representation of this states. So I cannot, I don't know. I don't know who are the operators that they will apply. Also, that will help for the measurement, for the question of the measurement. So I think that one has to have this map, and on this map, express this map in terms of Krauss operators, and then one can learn a little bit about what does it mean physically.
Yeah, one thing I just want to add in this aspect, Anamani. I mean, when you talk about what I understand that you talk about this CPTP map, right? Now, if you look at the classical network, also one has to somehow know that the corresponding map so that we can compare, right? Because
no, but it doesn't matter. Even if you put a map which is classical, okay, you will never go farther than this.
No, I'm not sure. But what I am saying that here, yeah, I mean, there I understand that in classical neural network that you describe, there is the framework is different than here. Although the ultimate goal is same because you have to pattern has to be somehow stored, right?
Yes. But for instance, if you have, imagine a classical set of neurons that they are 0, 1, okay? Yeah. And now you do a quantum map on that. This is indeed the paper of Ventura. okay, which he does it with the short algorithm, you will show that you can storage 2 to the n, okay? Okay, so it's the quantum nature of the map which will play there, okay?
So there is also, I mean, there are a lot of questions actually people are typing. So I guess I can at least take one because the Himadri Dhar, he is asking, is it possible to have a hybrid classical quantum neural network using unitaries and classical nodes? Naively, can this maybe allow some model for quantum learning? I think this is what you were just telling about this Ventura. Because
yes, well, I will say the following, okay? So that indeed it is known that this quantum Hopfield model, this was the paper of Lloyd that they show it, it's not very interesting for learning and so on, okay? So it's not very interesting. What I think, or what I would like to give you this idea is that maybe one has to think a little bit. So it's important to think the other way around. And this is something that I wanted, if you go home with something, message is like, the way to think about all these patterns and storage and memories, it's not to think how many I can have, exponential in the quantum case and linear, this is true, it's very important. But for me, it's more important, it's this, how many maps in the volume of all possible maps, how many of these maps I have. This is what it gives you power, okay? Because if it was like that, but you have a map, a single map, okay, find this map. Maybe this map, you cannot implement it physically even, no? I mean, but the strong thing is that the relative volume of these maps is large, okay? And this is powerful, okay? More than the other thing, which is also powerful, but normally the people keeps on this thing. So which is the storage capacity, exponential quantum, linear classical, this is very important. This is quantum advantage and all these things that now people talks about, but it's much more important to think physically and say, listen, you are, if you want, in a lab, all right? So which chances do you have to implement these maps? Well, if the relative volume of these maps goes to 0, so instead of going like if it was in the show, 1 over m goes like 1 over m to the 10th, it could have been, forget it. It's not helpful because that means there are so few that it will be impossible to implement them. But there are many, and this is important. It's exponential and there are many maps like that in the world. So.
Okay, so there are another 3 questions. Can I take, Anna? Do you have time?
Yeah, sure.
Okay. So then Rivu again asks, we are looking for different maps which have same number of stationary states, but the stationary states are different for different maps. So can the different maps be used to recognize the same pattern or that is stored the same memory?
Okay. Here there are several things. Okay, so each map can have a set of stationary states, and obviously this corresponds to the map because one defines the stationary states as the ones which are not changing by the action of the map. So if you change the map, it can be that you have another map which has other stationary states. If you have 2 maps that they have n orthogonal stationary states, these 2 maps that have to be related, now I'm going with usual by unitaries because both of them, they have n orthogonal states, okay? So this is the first part of the question. Then there is a second part, which I didn't want to talk here because it's already quite condensed, that you can say, listen, you have put as stationary states, pure states, but what happens if they are mixed states? Can I ask the same question, which maybe it's more interesting? How many mixed states can I storage with a CPTP map? Okay, and this question can be treated, and we have worked on that, but it's tricky in the sense that how do you define an ensemble of mixed states which are orthogonal? Okay, so this is not something that it's clear. And in order to demonstrate that there are maps like that, you need to work with an orthogonal ensemble. So you can reach these things. Another thing that I wanted to tell you, which is also related to that, it's that imagine that now you have a neural network, okay, which is with several layers, okay? And from one layer to another, you go by, of course, CPTP map. So you can ask so you can apply this kind of thing several times. So I have an input, which is the input neuron, and I have an output, which is the middle layer. And I want to know, okay, how many of these can be stationary? And now I apply it again. How many can be stationary? How many can be stationary? So you can apply that for this multi-layer neural networks or things like that. And this is related to other things which are a little bit more complex that we have to look a little bit.
Okay, so then Kapil asks, how do you think that Ising model is the ideal one to model the neural network? And he also asks why you don't choose the system of molecules rather than the spins.
Okay, so this is why I took a spin model. First of all, because it's very simple, and in the 80s you wanted to have the model of a neuron of the brain, and you know that the neuron either fires depending on the signal that it gets from other neurons or doesn't. This is like that, okay? So normally you take a binary system, and spin classical is a spin up, spin down, it's a classical system. You can take any other. You could take a molecule if you have this up and down, okay? Now you need to have, because these are attractor neural networks, there are other kind of neural networks which are not attractors, but if they are attractors, they have to have a landscape of energies which is with many minima, because these are the attractors. If it has a minima, it's not an attractor, it goes like there and there stay. So you have to have a Hamiltonian, whatever it is, for a molecule, for a spin or whatever, so that it allows to have interactions, okay, because with a single particle you don't have enough, and it has several minima. And this is typically a spin glass, but there are other models which will work equally well. So it doesn't have to be a spin glass. It's just because a spin glass is very simple, Hamiltonian is very simple, and you can write it, and then you see immediately that in order to be a minima, each spin has to update it, that it's the sign of the interactions of the others and so on, and it's easy. So if you do it with a system which is more difficult, you can do it probably, but maybe it will be more difficult to find it.
Okay, so if there is no other question, I can not see. So we thank Anna once more and give us time. So if Anna gives the permission, then can we take a picture so we can ask everybody to on their video?
Yeah, sure.
Okay, so Anna, could you please stop sharing the screen?
Yes, sure. Sorry.
Yeah, so please on the video and we can quickly take the picture, whoever is still online. Yeah, it's still showing sharing, but
I still use it. Sorry.
No.
Now.
Yeah, so Ganesh, can you take the picture? Yeah, so there are other people who are not, I don't know why, Bridge and others, can you please on the video, whoever is online? Priya. So there are more people, so you have to take several. So who is taking? Ganesh, are you taking?
Yeah, I'm taking screenshots.
Okay, so at least tell we should.
Oh, sorry. All right, Sohail. Okay. Yeah.
So there is Srijan, I think, which is Dell. Srijan, can he make online? May not be, but okay. Okay, so.
Watch Arun Bhaiya.
All right then. 3, 2, 1. Say cheese. Say it again. All right. That's nice.
Okay. Okay, thank you very much for joining us today.
Thank you very much.
We end today and we start again tomorrow at 9:30. And everybody, we will send the Zoom link also to all the participants and speakers and everyone. Now, essentially, we will send. Okay, so bye-bye. Good night. Bye, Anna. Thank you very much.
Bye-bye, Anna.
Bye.
Bye-bye.
Okay, great.